So hello everyone, welcome to our video. Today we have with us an amazing problem on Diophantine equations in number theory, which is one of my favorite topics. So let's take a look at the problem. Find all triplets x comma y comma p satisfying this equation x square minus 3xy plus p square y square is equal to 12p such that p is a prime number and xy are integers. So the equation is, let me write it down, x square minus 3xy plus p square into y square is equal to 12p. So if you have a good command on number theory, the first thing which should strike to you on taking a glance at this problem is to take mod 3. Why? Because then this term and this term will vanish out since they both are 0 mod 3. So taking mod 3, we get x square plus p square y square is equal to 0 mod 3. Yeah. So now I will write a statement and will prove it using by taking only examples. So the thing is a square is 0 or 1 mod 3. Why? You take a 0, it becomes 0 mod 3. A as 1, 1 mod 3. You take a as 2, 4, 4 is 1 mod 3. You take a is equal to 7, 49, 49 is 1 mod 3. You take 11, 11 square is 121, which is 1 mod 3, and so on. So this is a very important statement since with the help of this, we can conclude that in this particular equation, x square plus p square y square is 0 mod 3. We can get x square is equal to 0 mod 3 and p square y square is equal to 0 mod 3 because this is the only possibility. Otherwise, 1 plus 1 is 2 mod 3 and so on. So x is 0 mod 3, and then we can break this particular thing into two more cases, which is either y square is 0 mod 3 or either p square is 0 mod 3. But since the x is equal to 0 mod 3 case is common for both, so let's just substitute x is equal to, wait a minute, yeah, let's just substitute x is equal to 3q out in the original equation. So we get 9q square minus 9qy plus p square y square is equal to 12p. Yeah. So now let's take the case 1, which is y square is 0 mod 3 and p square is not congruent to 0 mod 3. So since y square is 0 mod 3, we must have y is equal to 0 mod 3. So we substitute y is equal to 3k in this equation. Let me highlight this. We substitute y is equal to 3k in this equation. So we get 9q square minus 9q into 3k. Sorry for the handwriting. Plus p square into 3k square is equal to 12p, which simplifies to 9q square minus 27qk plus 9, it becomes 9p square k square is equal to 12p. So we can cancel out a 3 and take everything common. K square minus 9k, no wait, it becomes 9, so it becomes 3k cube plus p square q k square, which is equal to 4p. Now observe that this is something 3 into say lambda, and which is equal to 4p. So let this expression k is q square minus 3k qk plus p square k square as lambda. So we have 3 lambda is equal to 4p. And since p is not congruent to 0 mod 3, which means this 4 must divide 3, which is obviously not true, and hence this results in a contradiction. My most favorite word in the dictionary. But anyways, we still have a we still have one more case to deal with. Case 2, and the case 2 is when p is congruent to 0 mod 3 and y is not congruent to 0 mod 3. Sorry, y square, and here it should be square, is not congruent to 0 mod 3. And since p square is 0 mod 3 and p is a prime number, so it will only be possible when p is 3. So that simplifies stuff a lot for us. So let's substitute p is equal to 3 in this equation. We have 9q square minus 9qy 9qy plus 9y square is equal to 36. So we can cancel out a 9 from here. Q square minus qy plus y square is equal to 4. And since y is an integer, so we can exploit this fact by forming a quadratic in y. So y square minus 9 minus qy, my handwriting is terribly bad, plus q square minus 4 is equal to 0. And since this is a quadratic in y, its roots must be integers, and for integer roots we have the condition the discriminant is equal to perfect square. Let this be n square. So the discriminant in this case is q square minus 4 into q square minus 4 is equal to n square. So which becomes n square plus 3 into q square is equal to 16. And which is a pretty simple casework. When we take q is equal to 1, when we take q is equal to 1 or minus 1, this becomes 3, this becomes 13. When we take q is equal to 2 or minus 2, we get this as 12, this as 4. So clearly this case will be rejected. Since n square is equal to 13 will not lead any integral solution for n. So we have q is equal to plus minus 2. And since we had assumed x is equal to 3q in the beginning, so we get x as plus minus 6 from here. So yeah, we have found out the values of x. Now, if we take x is equal to 6 in the equation, in the original equation, we have 36 minus 18y, and we are taking p is equal to 3, so it becomes 9y square is equal to 36. So we can cancel out this 36, and this 9 becomes 2y. So we get y is equal to 0 or 2. So for x is equal to plus 6, we have the solution triplets x comma y comma p as 6 comma 0 comma 2, 6 comma 2 comma 3. And for x is equal to minus 6, when we put x is equal to minus 6 again in our original equation, we get 36. Everything will be same except for the fact that a plus 18xy will come here, plus 18y plus 9y square is equal to 36. So from here we get after solving y is equal to 0 and minus 2. So we have find out the values of y, 0 and minus 2. So corresponding to which we have the triplets x comma y comma p as minus 6 comma 0 comma 3 and minus 6 comma minus 2 comma 3. So that's all the possible triplets in our question. So the final answer is x comma y comma p is equal to minus 6 comma 0 comma 3 minus 6 comma minus 2 comma 3, 6 comma 0 comma 3 and 6 comma 2 comma 3. So that will be all the possible triplets. So that was a fun problem to try, and so that's all the triplets for this problem. Hope you liked it. Do like, share and subscribe. Thank you.